Okay, so today we will be discussing decoder only architecture, and in decoder only architecture we are going to be discussing the GPT-1 family of models. Okay, so GPT-1 family of models, there is only one model, so it's not really a family. So let us see. Okay, so the vocab size of GPT-1 is 40478. It is space separated words. Okay, every word is space separated. This is the vocabulary size. The embedding dimension of the model, D model, is 768, right? The number of layers in the transformer block is, context size or sequence length is 512. Number of attention heads is 12. Activation function is GALU, Gaussian linear unit, right? Additional functions, dropout, layer norm, residual connections. Okay, this layer norm is called the pre-layer norm. Okay, I will tell you what pre-layer norm and post-layer norms are as well. Okay, so let us I will give you a brief overview on what the transformer layers is. देखो, in the GPT-1 architecture, there are 12 transformer blocks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12 transformer layers. 12 transformer layers. These 12 transformer layers get fed into something called as the LM head or language modeling head, which task is to predict the output token. Okay, the task of LM head is to predict the output token. And there is also this embedding layer in this section, right? Embedding layer. Embedding layer consists of positional embeddings and input to the model. Okay? Input to the model, as we have discussed, it is T cross D model. Right? It's a matrix. So the input to the model is T cross D. Here T is the sequence length, right? T is the sequence length to the model, and D is the dimension of the model, also called as the bandwidth of the model, right? So 512 cross 768, and when I say 512 cross 768, you must imagine a matrix of dimension 512 cross 768, where 512 are the number of rows, so this is, and 768 is the number of columns, right? So 512, this is for the word I am, right? And so on, whatever you decide to keep your words as sequences. And this is for your hidden dimension. For every word has a corresponding vector of its own, so it is the hidden dimension, right? So this is a scenario. So it is T cross D model. Now in here, in GPT-1 architecture, we do not use sinusoidal position embeddings, right? We do not use sinusoidal position embeddings. We use learned positional embeddings. So we ask GPT to learn the positional embeddings on its own. Okay, so in here you can see that, okay, this is the equation for learned positional embeddings. Okay, so WP is a weight matrix of dimension T cross D. Okay, to be added to here, right? To be added to here, we need the same dimension as this T cross D model, right? Let's see. So ideally, PT should the entire position for all the position P, it should be of the dimension T cross D model. Okay? Okay. So T cross D model. QT we choose for each position. Okay, for one single token. Let us see. Suppose for the token I, we initialize a position embedding. This is for the token I, which is QT. Right? QT. We initialize a weight matrix. like this. So the equation for the weight matrix will be, let me correct this quickly. QT, T cross 1. So QT transpose will be, bolo, 1 cross T, right? We will see why. This is for one word. It will be multiplied by a matrix of T cross D model. Okay? T cross D model. The output dimension T common for matrix multiplication will be valid. The output of the dimension 1 cross D model. Right? This is for one single token. This, right? QT. Now let us do it for all the tokens. Right? T cross what? For one token it is 1 cross D model, right? For T tokens it will be T cross D model. Fine? T cross D model. T cross D model. What is the dimension of the weights T cross D? And we know we only store weights for the learnable parameters, since we are only counting for the learnable parameters, that is the parameter count, right? We are only considering for weights, right? So T cross D model, T is 512, D model is 768, as we have discussed in GPT-1 architecture, right? 768, so it is 0.4 million, fine. And Qt can be anything, but in Qt, in this case of GPT, this Qt is a one-word vector, okay? Now, okay, let's see. We have to learn the input representation of each word. Each word consists 1 cross D model for one token, right? The input should be framed in such a way that two tokens that are similar. Suppose I tell you king and queen are similar, right? The dimension vector king and queen should lie within similar vector spaces. They say denote royalty, right? So on. So 1 cross D model, each vector. Suppose this is for the word embedding I. Let's not say I. This is a word embedding for the word king. It is 1 cross D model, right? And we have to build such a vector for all the words in our vocabulary. As we keep on training the model, maybe at a specific time it will only see T tokens. But as we increase the number of epochs, right, it will eventually see all of the data, and it will be able to build a token embedding for all the words in the vocabulary. For example, king, queen, right? 1 cross D model, right? 1 cross D model. Sorry, king will be like this. This is 1 cross D model. 1 cross D model. It's a number of rows 1, number of columns D. So D number of columns, right? This is for the word king, and this is for the word queen, right? 1 cross D model. So the words will be like this, huh? This is our new notation for now. 1 cross D model for each word. For building the entire vocabulary, or it will be for 1 cross D model for each token. For all the tokens in our vocabulary, it will be V cross D model, right? Where V is all the number of words in our vocabulary. So it is V cross D model. Fine. V is 40478. D model is 768. This comes out to be 31.1 million, right? And you can similarly see the equations for it as well. Et is equal to xc plus wa, as we have discussed in the positional embeddings part, learned embeddings part. Xc, v cross 1 for each token. This is the output token. You can do the matrix multiplication. It is easy, right? So input embeddings maps a discrete token to a continuous vector, right? We have a discrete token, king or queen. It maps to a continuous vector 1 cross D model, right? If cat and dog are semantically similar, their vectors should be closed in embedding space. This is number one. Number two, their embedding space should be structured in such a way that it helps our generation, right? Our decoding phase. Because ultimately these are being updated by backpropagation, right? So the backpropagation will update them in such a way so that it is helpful to our decoding phase. Fine? Okay, no issues till now. So the total learnable embeddings, you can see, it is 4 million, 0.4 million. From where? From the learned embedding space. Plus 31.1 million from the token embeddings, right? All of these are rounded off, by the way. So the actual numbers to show that. It comes to be around 31.5 million. Fine? No issue till now. Okay, no issue? Okay, the next part is the transformer blocks. You can see each of the transformer blocks, right? Each of the transformer blocks. not updated here, but I'll update it. In each of the transformer blocks, you have a constant stream of T cross D model going in. T cross D model. T cross D model. Where T is the number of tokens or input sequence length, and D model is the bandwidth of the model. Right? You can think of it, the bigger the D is, the more intelligent it is. Right? The bandwidth of the model, the more it is able to comprehend. Right? T cross D model. Everywhere you see, everywhere you see in any case of transformers, it will be what? T cross D model, right? Anywhere you pick, it will be T cross D model. In case of this, in case of output as well, it is T cross D model. T is 512, D model is 768, no issue. And there are such 12 transformer blocks. Okay, let us zoom into each transformer block. Okay, let us zoom into each transformer block. So this is what you get when you zoom into each transformer block, right? This is the input, right? This is the input. T cross D model. T cross D model. T cross D model, T cross D model, T cross D model. You can see this T cross D model is almost maintained in every block. Do you remember the standard decoder architecture? The standard decoder architecture will have masked, multi-head attention, adder norm, right? This is the H vector. We add a norm from here through an identity function. This goes into FFN. We have another what? Add plus norm. It goes into here through an identity function, and this goes into the next transformer block. Fine till now? Okay, see, is this what the architecture is? You can see, is this what the architecture is? Our input goes into 512, 768, add a norm, mask, multi-head attention, residual. You can see, right? It is the same thing. It is the same thing. There is nothing different about it, right? Now this has two components. Well, it is more than two components, but it has three components actually. Mask, multi-head cell retention, layer normalization, FFN, and again this is another layer normalization. So three components it really, right? Each transformer block comprises of mask, multi-head retention, layer normalization, FFN, and another layer normalization with the residuals coming here like this, right? Now what I will say, the purple arrows, right? The purple arrows indicate zooming in. The green boxes you can see, right? Green boxes always represent the learnable parameters. When I calculate the learnable parameters, the green boxes will always represent the learnable parameters and where the weights are being changed, where the weight component is, okay? So let us see our first component, which is the mass multi-head cell retention. By the way, before we proceed, you can see this is how transformer block L1 gets fed into transformer block L2. Fine, this is what is actually happening. The transformer block L1 through T cross D model, right? Same thing as that we discussed. It gets fed into this transformer block, and everything is T cross D model. Fine? No problem till now? Okay, let's see mass multi-head cell retention, okay? We will discuss each. This is what you get when you zoom into mass multi-head cell retention, okay? This is the part. Mass multi-head cell retention has certain components, right? This is the input, no issue. This is the input of dimension. Actually, it should be like this, right? It should be like this, not that, because input is outside of the transformer. T cross D model, right? 512 cross 768. This gets split into 12 attention heads. So inside the layer there are 12 layers. Inside each transformer, inside each GPT-1 there are 12 transformer blocks, L1 to L12. Inside L1, in the MHSA, mass self attention, there are 12 attention heads. So there are two different 12s here, and they are different, and you can choose them to be different. For example, you can choose them for be in the next example when I explain GPT-2 architecture, we'll see how we will change them. Okay. So the input is T cross D model we have discussed, right? So what we do, we split it. I will tell you how we split it, but note that it is going to each, right? Each, and we concatenate them. We'll concatenate them. I will explain again everything. This is just giving you a brief overview of what is going on. We apply a linear layer. We apply a dropout. Linear layer is learnable, as you can see from the green part, and this gets fed into the next. Okay, let's discuss each attention head. We are going to zoom in to each attention head. Let us zoom into attention head A1. Fine. So this is the attention head A1. Again, this should be somewhere here. We initialize W1 Q. This is too small for it. We initialize W1Q, right? Here the lower index represents the attention head number. So if it is W12, it is the attention head 12. It is W7, it is the attention head 7. Okay. This lower index represents the what? Head number. Q represents whether it is a part of Q query, key or value. It is sample from a normal distribution with zero mean unit standard deviation, right? We sample this W randomly. So what do we use in Python? Random dot random, right? Right? We use this to sample it normally, right? Random dot random. Okay? Similarly, W1K is also sampled like this.
How did that 768 plus 16?
Yeah, I will explain. I'm just going through what it exactly is. Right? W1K. Same thing, we are sampling it is 768 into 64. Right? This will be much more clear. We are just sampling random weight vectors like this. We are just sampling random weight vectors like this. Okay, in here, see. What was D model? D model 768, right? We choose dk is equal to dq, right? Such that that is equal to db, such that it is equal to d model divided by n heads, number of attention heads. Let us see, let us plug in. Number of attention heads is 12. D model is 768. It comes out to be 64. Right? This is where the number 64 comes from. Through this formula. Okay? This is where the number 64 comes from. Is it clear till now? Is this 64 number where it is coming clear? Okay? So in here it is going T cross D model, right? T is 512, D model is 768, T is 512, D is 768, right? The equation you see for each of them. Q1 is equal to H W1Q, right? Let us see. The dimension for H is coming. H is denoted by the input H, right? H is 512 cross 768. Should draw it somewhere else. H is 512 cross 768. Fine, no issue. Matrix multiplication with W1Q, W1Q. W1Q's dimension is, बताओ, 768 into 64. 768 into 64. Fine. For matrix multiplication to be valid, these two must be equal. The output for this matrix multiplication will be 512 cross 512.
Plus 64.
Yes. 512 cross 64. Fine. So the Q's dimension will be 512 cross 64. This is what it is written. Yes, no? Similarly, H dimension 512 cross 768. W1K's dimension 768 into 64. For matrix multiplication to be valid, these two must be equal. The output will be 512 cross 64. Yes, no? So K1 is 512 cross 64. Is it clear? No? No issue. Okay, next. Same thing will be, right? V1 will be 512 cross 64. So each of them is 512 cross 64. Right? We have discussed what is Q, how does Q, K and V comes to, right? We have discussed how does Q, K and V comes to. We have discussed this weight matrix, 768 into 64. I have discussed where this number 64 comes from, right? It is just D model divided by n hence, right? And we have also discussed that this Q1 ka dimension is 512 cross 64, Q1 ka dimension 512 cross 64, V1 ka dimension 512 cross 64. Fine. So in here you will have Q of dimension 512 cross 64, K of dimension 512 cross 64, and B of dimension 512 cross 64, right? We have discussed this. No issue till now. QKV. We have discussed this. Attention A1 also equals to alpha V. Right. In the previous classes we have discussed attention in very great detail. I have discussed how attention works. What is this part? What is this DK? What is this M? What is this KT transpose? I have discussed each individual part of attention. Hope you remember. So Q1, K1. What is Q1? Right. Q1, V1. What is this? One represents the attention head index. Right. This is for the first attention head index. Right. So A1, first attention head index. Let us see. Q1, K1 transpose, right? Q1 dimension 512 cross 64. K1 dimension 512 cross 64. उसका transpose 64 cross 512, right? 64 cross 512. For matrix multiplication to be valid, this should be same. It is same. The output dimension will be 512 cross 512, right? 512 cross 512. So इसका dimension क्या है? 512 cross 512. We are dividing by DK. It's element wise division. So the division, so each element is divided. So everything remains the same. Dimension doesn't change. We apply a masking. Why is masking needed, Mrinal?
So that for the decoder to actually, so that it does not know the future output, like future token, and it can reason and give out a.
We apply a what? We apply masking में we apply a upper triangular matrix, right? we apply whatever it is. We apply an upper triangular matrix, right? This we have also discussed. Masking in details we have discussed. We apply a upper triangular matrix so it doesn't stare at future tokens and just predict the identity function, right? We apply an upper triangular matrix divided by dk, square root of dk. Should be square root, not dk. This should be square root of dk. Okay, square root of dk. Why is square root of dk important? This is variance scaling, right? We have also discussed where the square root of dk comes from. It comes from expectations, right? It comes from expectations of q1, k1 transpose. We have discussed this, right? Masking is applied so that it doesn't stare into the future tokens. V1, it broadcasts into the hidden dimension of 512 cross 764, no? 64. Sorry, 64. 768 cross 64, yes. So I have told you, I should interrupt this anyway. So Q1 is 512 cross 64. K1 is 512 cross 64. V1 is 512 cross 64, right? This is what I have discussed till now. So Q1 K1 transpose divided by square root of dk plus m. Matrix for matrix multiplication to be valid, the dimension of this should be equal to the dimension of this, right? Sorry, additive. It must be equal. Both of them must be equal. So this is 512 cross 512. This should be 512 cross 512, right? And it will add easily, right? Whatever this is, let's say this is as alpha. The inside term we are going to term it as alpha. So up till softmax, right? Softmax also element wise, no issue. Softmax element wise, so it doesn't matter. It will be 512 cross 512. So we have the 512 cross 512 matrix, right? For alpha. For alpha we have a 512 cross 512 matrix. This is the alpha. Alpha is softmax of Q1 K1 transpose divided by square root of dk plus m, right? This is alpha. And V1 का dimension क्या है? 512 cross 64, right? For matrix multiplication to be valid, this two needs to be the same. The output dimension will be 512 cross 64. So A का dimension है 512 cross 64. The A's dimension is 512 cross 64, right? A's dimension is 512 cross 64. This is what we get output for the attention end, right? Now let us see the total learnable parameter, right? In total learnable parameter we have W1Q, W1K, W1V. These are the learnable parameter in each attention head, right? In each attention head. This is the learnable parameter. So it will be just 768 into 64 for 1 into 3 for K, Q and V, right? This is the number of learnable parameters. If you do the calculation, it will come out to be around this figure, 0.147 million parameters, okay? This is for one attention head. And you can see simultaneously, there are 12 attention heads, fine? This is for attention head number 2. Same thing, not that much different. Same thing, input 512 cross 768. We are getting weights of each of 768 cross 64. We are doing all the attention stuff, right? Similarly, it will be 174 by 7. This is for all the attention heads, right? All the attention heads. There will be 12 such attention heads. You can see there will be 12 such attention heads. This is for the A12, right? You can see it is indexed by 12. You can see it is indexed by 12 now. So for each attention head, there will be such, right? What is the total number of parameters for the attention heads? Can you tell me? 0.147 into 12 m. right? Whatever number of million parameters are there, right? It comes out to be,
Why 12?
huh?
M why 12?
Well, there are 12 attention heads, right? 12 attention heads. For 12 attention heads into 12, this comes up to be the figure 1.769 million. Okay? Fine? No issue? So, what we do, okay, we have 768 into, sorry, we have 512 into 64, right? From each attention head. A1 ka dimension we have discussed in the past. 512 cross 64, right? This is 512 cross 64, 512 cross 64, 512 cross 64, right? These are the dimensions. So we have 12 such 512 cross 64 dimensions, right? This layer concatenates them. The task of this layer is to convert this from 512 cross 768. This is also, if you think about it, this is also where the formula comes from. dk is equal to dq is equal to dv, that is equal to d model by n heads. This is where also the formula comes from. I don't know what I wrote here, but okay. This is also what the formula comes from. Okay? To be transposed, we change the dimension of n head into t into dk, n head cross t into cross dk to t cross d model. Okay? See this. N head cross t cross dk, right? To t cross d model. This is the same, no issue. So n head into dk should equal to d model, right? So dk should be equal to d model divided by n head. This is where the formula comes from, and we have chosen dq and dv to be the same as dk, right? This is our choice. dq and dv must be the same for attention to work. dv is our choice, we can choose it anything, but this is we have chosen to be equal in GPT-1. Fine? No issue till now? This is where that formula comes from. We concatenate them. After we concatenate each attention head, the task of each attention head is what? To capture different aspects of the sentence, right? Capture different representations of the particular sentence, right? To capture rich meaning, individual different meaning. We have each individual different meaning concatenated along a dimension, right? 512 cross 768, right? But however, we have just concatenated them, right? We have just concatenated each. We haven't gave them any chance to communicate within each attention head, right? We haven't given a chance them to communicate, to reason, right? This is the task of this linear layer. To give them a chance to talk to each other. To say, okay, I captured this representation, what about you? Okay, you captured this representation. How can we utilize each other's communication to make the representations much more useful, to make the decoding much more useful, right? To make the generation much more useful. When I use decoding, when I use generation, they mean the same thing. They are just different. They are just the same words, right? So this is what we do. The input from here is 512 cross 768 or T cross D model. Fine, we are going back to this T cross D model as we have discussed. This is the bandwidth of our model, right? T cross D model. So MHSA, I am going to represent this as Z. I should have represented this as A1, not Z. Okay, anyway, I am going to say A1 is T cross D model, right? A1. will zoom into it. A1, yeah, the input to this layer is T cross T model. Yes. This is A1. This is not there. This is A1. This is A1. A1. This is called up projection. Not up projection. Sorry. This is called linear projection. This is called linear projection. Linear projection. So A1 is T cross D model. MHSA is defined as A1WO. You can see we are not taking any biases here. All these equations, by the way, we are not taking any biases. It's simpler in this sense to just omit biases and discuss. But you can add biases easily. It will be something like B, and you can determine what will be the dimension of B. That WO is of the dimension since okay, the output to here, right? The output to here should be T cross D model, right? So MHSA output should be T cross D model. Why? This is the common bandwidth of the model, right? This is the common bandwidth of the model. The output should be T cross D model, right? WO's dimension, since we need the output of this to be T cross D model. A1's dimension is from the previous input is T cross D model. For matrix multiplication to be valid, something cross something, this should be the same as this D model. Cross what? What do we need the output? We need the output to be this D model. So it should be D model here as well. D model. So the dimension of WO should be R of D model cross D model. D model cross D model, the output, the dimension of WO should be 768 cross 768. Fine. MHSA, as I discussed, T cross D model, bandwidth of the model. Same. Okay. Number of parameters in linear. What is the learnable parameter here? WO 768 into 768. It comes out to be 0.559 million parameters. Total learnable. Let's see. You can see this is for each attention head, right? Each attention head. It comes out to be 1.769 million. For the linear layer itself, it comes up to be 0.59 million. Right? We have discussed this 768 into 768. So total, if you add them up, it will be 2.36 million parameters per masked MHSA block. Per masked MHSA block, it will be 2.38, right? So we have discussed the masked MHSA now. Masked MHSA is clear. You can see 512 cross 768 T cross D model. This gets fed into layer normalization, right? This is the residual, right? I am going to denote it as H. You fit H in here, you fit the mask MHSA from here, and you take the layer norm. This is called a pre-layer norm. Okay, this is called a pre-layer norm. And this H plus layer norm of masked MHSA of H is called a post-layer norm. Post-layer norm. H is outside of the layer norm function. हाँ देखो ये function number 1.
It's not in the diagram.
This is not in the diagram. This will come in the GPT-2 architecture. I'm just giving you telling you what is pre-layer norm and what is post-layer norm and nothing else. ओके, ये अंदर आता है ln of h plus mask MHSA, mask multi है self attention of h function, right? This is called pre-layer norm. H plus layer norm of masked MHSA of h. This is called post layer norm. Okay? Can you tell me what would happen? Actually, yeah, I'll cover this in GPT 2, not GPT 1. Anyway, it's going like I said. And we have also discussed what layer norm is, right? No issue. This gets fed into the FFL layer. Right? For what? For reasoning. After layer norm, right? It will have some residual. It will reason and de-reason, right? We'll take a look into each of them. I'm just going through and we do layer normalization again, which gets fed into the next transformer block. Okay, let's look inside the layer norm. Let's look inside the layer norm layer. Layer norm of H, right? Layer norm of H is gamma. Gamma is a learnable parameter plus H minus mu sigma into beta. Fine? Sorry, not into, plus beta. Right? This is the de-scaling operation. This is the de-shifting operation. Fine? This is called a de-scaling operation. This is called a de-shifting operation. Layer norm normalizes across the token dimension, not the feature dimension. I will discuss this. Layer norm normalizes about the token dimension and not the feature dimension. Okay. So I'll briefly go over what layer norm is again that day. Okay. So let us discuss what layer normalization is. We have an input of T cross D model, right? T cross D model. T is what? Number of rows. Right? So it is like I am eating ice cream. That. Right? So I want you to forget everything that I told during that day about patch norm and layer norm. Okay? T is the number of rows. T is the number of rows, right?
What is T though?
T is the sequence length.
Yes.
Sec length. Sequence length. Or in other words, rows. D model is the dimension of the input vector, right? Or the dimension of a model. Right? This is the D model. This is the sequence in T. No issue till now? No issue? T cross D model, right? For each there is D model. Now in batch norm, what we do? In batch norm, we calculate the mean of this entire thing, mu batch. Right? We calculate the standard deviation of this entire thing, sigma batch. Fine? Sigma batch. In this case, the pad will be 0, 0, 0, 0, 0, whatever, right? Whatever you choose, whatever you initialize, minus infinity, whatever you initialize, right? It will affect the mu and the batch as well. Why? It will not, mu is what? Xi, sigma xi divided by n. N is still increasing now. You have to still count for the number of pads, right? So n is still increasing. This padding will affect these tokens, the mean of these tokens. Ideally, what do we want? Ideally, we want them to be, normalized independently. Ideally, we want such that these padding tokens will not affect the representations of I am eating whatever, right? So what we do? T cross D model, right? So this is normalizing across the feature dimension, right? What we do? We normalize like this. We choose just the word I to be normalized. इसका क्या होगा? Mu, some mu h1, right? Sigma h1, right? For I it will be d model, some d model, right? It is 1 cross d model, 1 cross d model, right? We normalize it for this, for the word I, sum xi divided by n. N will be the d model. This way the padding tokens, these are completely independent of the padding tokens. Padding tokens will not even play a role, right? Padding tokens will not even play a role. So this is independent. So this will just normalize across this. Okay? This will completely get rid of this padding tokens effect, and it will be independently normalizable. So normalizing 1 cross d model. Fine? No issue till now. This will have some different mu h2, sigma h2, right? It will calculate some h minus mu h2 divided by sigma h2. Fine? No issue? Clear till now? This is what layer norm versus batch norm is. Fine? Now in layer norm of any vector h hat is defined as gamma multiplied by mu h minus mu. This is the inside part, which is the normalization part, and this is the denormalization part, right? Scaling, shifting, descaling, shifting, right? As we have discussed, h is 1 cross d model. Remember to that layer norm, 1 cross d model, right? Gamma will be d model of dimension 1 cross d model or d model cross 1, whatever you choose. It is the same thing. It's a you can choose it to be anything, right? Beta, it is 1 cross d model or d model cross 1, doesn't matter. It is 768, this is 768, right? For matrix multiplication should be valid, everything must be the same. This addition must be equal, right? Whatever this is, right? This and this dimension must be the same. This is 1 cross d model, 1 cross d model, 1 cross d model, 1 cross d model. The output will be 1 cross d model. 1 cross d model and 1 cross d model, right? Everything is along the vector dimension now, not matrix anymore. Vector dimension. So gamma, it is 768. Beta, it is 768. Number of learnable parameters 768 plus 768, 1536. Fine? No issue? This is a layer norm. Residual, as I have discussed, h dash. H, the input identity function, right? Plus mask MHSA, right? H is T cross D model, this is T cross D model, no issue. No learnable parameters here, only learnable parameters here. That's the layer norm, right? Anyway, we have discussed the layer norm. No issue, 512 cross 768. The output is 512 cross 768. The residual we take. Next is the FFN, right? Feed forward network. Okay, there are two different architectures. As I told you, right? This FFM is a what? Inverse bottleneck layer. It's an inverse bottleneck layer. Yani we take the present representation, we expand it to higher dimension, we compress it back down to its original dimension. This is the inverse bottleneck layer. Fine. So H, the dimension we have been working with till now, the input to the model, what will it be? 512 cross 768, the bandwidth to the model. Fine. I told you we expand it 4 times, right? X expansion, right? So the output representation will be 512 cross 3072. 512 cross 3072, and this 3072 is just 4 into 768. Okay, we expand it 4 times. So 512 is the number of tokens T. 768 is DFF. DFF. We are just saying another variable name, right? I am running out of variable names, but okay. So H dash W1, H dash is the input now, plus B1, right? This H dash comes from the layer now, after the layer now, right? Since hence we are naming here as H dash, right? H dash plus W1 plus B. H dash का dimension 512 cross 768. W1 का dimension कुछ होगा, let's see later. B1 का dimension कुछ होगा, let's see later. We know the output dimension, whatever it is, right? Let's say it as some anonymous variables there, right? कुछ होगा, कुछ भी नाम दे दो, no issue. Give any name. This output dimension is 512 cross 3072, right? 3072. We are expanding here, right? Output 3072. 3072. For matrix multiplication of this to be valid, can you tell me what is the dimension of W1? 768 cross good 3072, right? For matrix multiplication to be valid, this and this must be the same, and this too from the output, so it becomes 512 cross 3072. Fine, no issue. This is the first part of the bottleneck. We are expanding it, right? We are expanding it. Next part of the bottleneck is to contract it back to its original dimension, right? Contract it back to its original dimension. So this (4x) expansion back to its original dimension. The original dimension is 512 cross 768, right? Let us say z dash, some another anonymous variable. We don't care. Oh, by the way, before we, by the way, after the expansion, right? After this expansion, we just take a Gaussian linear unit. Notice, this is just another non-linearity. Fine. This is just another non-linearity. Anyway, continuing, we take the Gaussian. Notice. By the way, I have not discussed the B1 dimension. Okay, let's go back to this. I forgot some things. Let's go back to this. I forgot some things. Okay, so we have discussed H dash W1 plus B, right? I have told you that W1's dimension will be 768 into 3072, right? H dash ka dimension 512 cross 768, right? This is the dimension C law. Can you tell me the B1 ka dimension? B1 is a vector now. Okay, I'll tell you what. Ideally, it should be what? 512 cross 3072, right? For addition to be valid, this is we take. For addition to be valid, this should be the case. But we don't take this. We take just this 1 cross 3072. My question is why? My question is, sir, why? ऐसे क्यों हो गया? Right? It sounds odd. We just take a vector. Sorry, yeah. B1 3072. I got confused. We just take a 1 cross 3072 or 3072 cross 1. Doesn't matter. It's a vector. We can broadcast it to any dimension. The answer to this is broadcasting. We can just broadcast this. Do you know PyTorch and how PyTorch and NumPy uses broadcasting? Right? If you need to 512 cross 3072, if you want to add it to 3072 vector, into 1, right? It will copy it 512 times. It will copy it 512 times into 3072. It will automatically do it in the. It will automatically do it in NumPy and PyTorch. It will just copy the value. Suppose this is B1, right? B1, 1 cross 3072. It will copy it 512 times within the same value. So it will just broadcast it as that necessary dimension. This ensures that we save the number of parameters. And we use one B1 for entirety, right? And on top of that, we add a non-linearity gain. Fine till now? No issue? Okay, we have talked about expansion, right? 4x expansion. Now we will say, since this is 4x expansion, it will be 4x contraction as well, right? 4x contraction, right? 4x expansion, 4x contraction. Simply, it's an expansion, contraction. It's a what? It's an inverse bottleneck layer. So the output we need 512 cross 768, right? 512 cross 768. It's a what? It's the original bandwidth of the model. This is the output. Let's say some anonymous variable z1 dash. So I have told you that this is just from the output from the previous. This we are saying as z1, right? This is z1 dash, by the way. z1 dash. Okay, z1 dash is equal to z1, whose dimensions are 512 cross 3072. W1, W2 plus B1, B2. Fine. This is Z1. We have to find this dimension is 512 cross 768. Can you tell me the dimensions of this? For matrix multiplication to be valid, it should start with 3072. Fine. For matrix multiplication to be valid, 3072 into what do we need? 768 as output. 768, right? We need 768 as output. Is matrix multiplication valid? Yes. What is the output? 512 cross 768, which is the original one. 512 cross 768. This is what we needed, right? So W dimension is 3072 cross 768. And similarly, by the broadcasting rules, what we have discussed in the past, B2's dimension will be 768 dimensional vector, right? So W2 is a 768 into 3072. 3072 into 768 vector dimension matrix. So let us see the and you can see we do not apply a non-linearity on top of this. There is only one non-linearity, which was in the first expansion layer. There is no non-linearity in the contraction layer. We want to pass it down without any compression to the original layer norm, because layer norm will normalize it again. Yeah, let's see in here what is going on. We are passing this FFN into this layer norm, right? Layer norm will automatically normalize it as needed. We are not passing it any non-linearity. See, no non-linearity in the second function. Yellow is only applied in the expansion layer. It would squash the output before the residual connection. For the expansion, W1 was 768 into 3072 cross vector, right? It comes out to be, if you multiply it, this much. V1 is 3072. 2.359 million. Contraction 3072 cross 768 matrix. Comes out to be this much. B2 768. So the total comes out to be 4.72 million. Clear till now? Any issues? We have discussed the FFN, and same thing with layer norm. There is another 100 36 learnable parameters, right? And again, we have discussed the residual as well, right? FFN residual. So again, going over it again, mask images, layer norm, FFN, and layer norm, right? We have discussed each of these components. Let us see the totals. Total learnable parameters for mask MHSA is this much. Fine. For layer norm 1, it is 1536. For FFN, it is 4.72 million. For layer norm 2, it is total comes out to be 7 million. Okay. For each transformer block, total is 7 million. For 12 transformer block, it will be 12 into 7, right? Comes out to be around 84 million, I think. Yeah, around 84 million. And this is the same. Sorry. This is changing. This is the same. This is the second transformer block, right? This is the second transformer block. We do the same calculations. It is repeated. Last is LM head, right? LM head predicts what? Probability distribution over the next token or the vocabulary, right? It predicts the probability distribution. H12. Okay? When I say H12, that means the input H has been modified by each transformer layer 12 times. For each 12 layers, right? It has been modified by each. H is T cross D model. Ignore this is wrong. Ignore this. T cross D model. So T is 512 cross 768. It should be 512 cross 768. We need the output over a vocabulary dimension, right? We need the output to be over the vocabulary dimension. Vocab. Right? Just for the sake, I'll tell you WE is V cross D model. Right? O is T cross V. T cross V. I'm just telling you the dimensions right now, I'll explain. O is equal to H12 WE transpose. Fine? WE transpose. No issue till now. The vocabulary is 40478. Right? 40478. Right? H dimension, as I have discussed, it is T cross D model. 512 cross 768. WE dimension is, as I said, it is WE's dimension is this. WE's transpose dimension for matrix multiplication to be valid 768 into 40478, right? These two are equal, matrix multiplication to be valid. The output will be 512 cross this much. Is it clear? However, we wanted 1 into 40478. We wanted this, right? We wanted a probability distribution over the output vocabulary, right? We wanted one vector such that it is given 0.1 for the first word, 0.7 for the second word, 0.05 for the third word, and so on, right? We wanted this ideally, right? So we just throw it away. It is 512 cross 768, right? We just pick the first one, and we throw away the rest, right? Otherwise, it is equivalent to what? Otherwise, it is equivalent to me asking you, give me 3 sentences in parallel. To a human, give me 3 sentences in parallel without having a concurrency. I tell you, okay, this is the sentence number 1 for me. Based on this sentence, predict 3 sentences in parallel. We are asking this to the model. Predict 3 sentences in parallel. A human will not be able to do it. This is the equivalent analogy for a model. If you do 40478 into this, it comes out to be around 31.1 million parameter, okay? And logits is 1 cross 40478. If you do this, it comes around to be 31.1 million learnable parameters, right? But I didn't color this in green. You notice this, right? I didn't color this in green. That is, this here parameters are not learnable actually. Yes. Now why do this? You see, trace this arrow. Now I'm going to trace this arrow. This arrow, okay? Alright. Same thing, WE. W is dimension. B cross E model, same dimension. That's interesting. We use this WE. Here it is WE. There it is WE transpose. See, WE transpose. We take the transpose of WE. This is called wait time. This is called wait time in GPT architecture, okay? We tie it to the token embeddings we have discussed. This 31.1 million. Same dimension, 40478 into 768. Reasons why we tie this. Number 1 is to save the number of parameters. We'll save 31.1 million parameters by doing this. Reason number 2, they are essentially doing the same thing. For here, see how it maps a discrete token to a continuous vector. If cat and dog are semantically similar, this vector should be close in embedding space. This looks at the continuous hidden vector H12 and determines which token it represents by computing a dot product similarity. Right? Dot product similarity between the entire representation and the last token. H12 with respect to what will be the most likeliest. So they are similar in function. So if the hidden vector means furry domestic pet, the score is highly likely to be cat and dog, right? So they are essentially doing the same thing. They are competing for the same function, which is a dot product similarity. They are essentially maximizing for this dot product similarity. Hence, we can reuse this. Eventually, backpropagation will do its magic. It will adjust in such a way that this wait time and that, right? It will adjust in such a magical way. And don't ask me how, because no one knows. Because the magic of backpropagation. It will adjust in such a way that it is able to use that. Maybe we might have better representations, but it will take longer to train. It might take, if we take a different learnable parameters, let's not take WE, let's take WO or WL, right? Or WD, right? Learnable parameters. It might learn, it will learn the same thing, it will almost learn the same thing, you notice. Right? These are empirical things. And I don't have a mathematical explanation on why we do this, but this is the intuition behind what we do. Why we do. Okay? Clear till now? For each transformer block, this was around 7 million, right? 12 into 7 million, 84 million. Embeddings is 31.5 million. Embeddings itself is very gigantic, you can see. If you add add another WD there, right? It will be 2 into 31.5. हाँ? किसमें? ट्रांसफॉर्म में? No.
31.1 ऐड किया था.
नहीं. Because it is 7 into 12, right? 7 into 12. Right? These are kept separate. This was 31.1. This was in the token embedding layer. This is in the embedding layer. In the embedding layer it is 31.5. In the transformer block it is 7 into 12. 84. In the LM head it is 0. So total if you do, it comes out to be 115.5 million. The actual number is actually 117 million. Why? Because of rounding. We have rounded a lot of numbers. Second thing, the projection biases. We have ignored all the biases. If you add the biases, now the actual number which is reported is around 117 million parameters. This is GPT-1 architecture. This is GPT-1 architecture. Is it clear till now? I'll go over it again. Right? I don't know. I'll go it in a summarized way. So this is the embedding layer. Embedding layer gets fed into the embedding layer consists of two parts: the positional embeddings and the token embeddings, right? T cross D model. There is the input. T cross D model is also the banded order model. It passes through 12 transformer blocks and it passes through LM head. In each transformer block, there is a mask MHSA. Mask MHSA goes into layer norm goes into FMN. FMN goes into the second layer norm. The layer norm consists, the mask MHSA consists of input passing to 12 attention heads. 12 attention heads, we concatenate them. We pass a linear dimension and we give a dropout. Then it goes to layer norm. Layer norm has residual and layer norm. There are 12 such attention heads in mask. There are 12 such attention heads in mask MSSA. Each of the 12 can be represented like this, KQB. And after all that, it passes through an FFN which comprises of expansion and contraction layer, which is also called the inverse bottleneck. This gets passed through a layer norm and this gets fed into the next transformer block. After all of this, it gets fed into the LM heads whose weights are tied to token embeddings, which are learned, okay? Token embeddings which are learned. This is the, if you zoom out, this is the GPT-1 architecture. This is the GPT-1 architecture. This is a decoder only model. There is no encoder here. Okay? There is no cross attention here. Now I'll tell you the differences between GPT-1 and GPT-2 XL architecture. This is the XL version, extra large version. The difference is of course of the numbers. The vocabulary now is 50 to 57. This increases from 404 something to us, right? It increases. The embedding dimension, D model is 16,000. Transformer block and layers is 48 now. Context size 1024. Now my attention is 25. The configuration changes. We have Galuna. We have dropout post layer norm, as I have discussed in the past. Post layer norm. Residual connections and BPE, byte pair encoding, right? Second thing, now weights are no longer initialized from 0 and 1. 0 means unit standard deviation. Weights are normalized from 0 mean 0.02 standard deviation. You ask me why? I don't know. No, honestly, I don't know. Like this is what I found out empirically to work better. This we have initialization methods such as Xavier and E initialization, but this don't lie in the Xavier and E initialization means. But this is some arbitrary number. I don't know actually where it comes from. Right? If you find out, please tell me. But we initialize from there. Now you can see we have 48 transformer blocks. All the differences are marked in red. Okay? Now we have L1, L2, everything is same, but we have 48 transformer blocks. Input data model T cross D. Now it is 1024, 1600. Right? If you calculate it, it comes to be, all these calculations are given. You can go through them. Right? All these calculations are given. I am just going through the differences. Right? This is also different. H48 no, it is not H12 anymore. It is H48. This is different. Right? It is 1 cross 50257. It is, the number is different, right? Inside each transformer block, this is the difference. Layer norm is post layer norm. I have discussed, told you, right? Why do we do post layer norm? In pre layer norm, it was in pre layer norm. This is our example of post layer norm. In pre layer norm, it was Ln of H plus masked MHSA multi-head self-attention of H, right? This was pre-layer norm. This is post-layer norm. Okay? In pre-layer norm, you can see we are adding it to the inside and then we are normalizing it. In post-layer norm, we are not modifying this. What does that mean? We are keeping the residual signal intact. We are not we are not modifying the residual sleeve. And this was the point of residual condition, to pass it down without any modification, right? We have seen in ResNet, we have seen in ResNet architectures, that was the entire point. Pass it without any modifications. So this is what we idealize it to. We take the layer norm of masked MHSA, we are normalizing the masked MHSA, and we are just adding it via an identity function here, right? We are just adding it via an identity function here. We are not modifying the input residual connection. That is the point. Another few difference, huh? So layer norm is modified. Equation of layer norm is modified. Another difference when you come to FFN, right? Specifically the W2. This is initialized like this. It is drawn from a zero mean, 0.02 divided by number of n layers, standard deviation. Okay, the official explanation of this is to combat the layer growth. As your layer growth increases, it will contribute to exploding gradients. So this is the official explanation. How did we come to this number? It's empirical. I can't tell you. It's empirical. They have done studies. But know that we sample it like this. W2 we sample it like this. Very specific here. I don't know why it's so specific. W2 is sampled like this. Not W1. W1 is sampled from that 0 and 0.02. It is still sampled like this. Even in mass MHSA, this W, right, linear layer, is also sampled from the same thing, 0 and 0.02 divided by n layers. It's sampled from the same thing. Now the attention heads are no longer 12, it is 25. This is where the different number shines. Earlier it was 12, right? It was 12, now it is 825. Right, this is where the 25. Number of attention heads is 25. Numbers of layers is 12. This is another difference, right? And if you calculate the total, right, it comes out to be 1.5 billion parameter models. Same thing, do the same treatment to GPT-1, it comes out to be 1.5 billion parameters. This is the GPT-1 and GPT-2 architecture, right? Is this clear till now? No issue?